So now we're going to look at an example where the end behavior asymptote is not going to be a horizontal line. So we're going to have to do a little bit of calculating and thinking to determine what the end behavior asymptote is in this example. So let's start this example like all the other examples. Let's factor our rational function, factor the numerator and the denominator. So the numerator factors the quantities x minus 4 times x plus 4. Is x squared minus 16, that's a difference of squares. The denominator is just the quantity x minus 2, that does not factor. So one thing we'll notice here is that there are no holes in this function. None of these factors cancel out. So there are no holes. So this, where it says right without the holes, I mean, there's no cancellation, so f of x is factored and simplified there. So now we have to determine the x-intercepts, the y-intercepts, the behavior asymptote, the vertical asymptote, all of the information about the function. So the x-intercepts, remember you want to look at where the numerator is 0, because when the numerator of this rational function is 0, the whole function will be 0. So it looks like we're going to have x-intercepts at 4, 0, and negative 4, 0. 4 and negative 4 are the x values that would make the function equal to 0. The y-intercepts, we just need to evaluate f of 0. And notice I can evaluate using the factored form of the function or the original form of the function, sort of my choice. So we get negative 16 divided by negative 2 is 8. So it looks like the y-intercept is 0, 8. I'm going to skip the end behavior asymptote and do the vertical asymptote, since that's a little bit easier. Looking at the denominator here, it looks like the only value that x cannot be is 2. So it looks like at x equals 2, we're going to have a vertical asymptote. Now for the end behavior asymptote, notice how, looking at this function, Miss Adams did a video on this earlier, the degree of the numerator is 2. The numerator is a quadratic function, and the degree of the denominator is 1. The denominator is just a linear function. So that means we're going to actually have to divide x squared minus 16 by x minus 2. We're actually going to have to do that division. So we could do long division or synthetic division. That's our choice. I'm going to choose synthetic division. So remember, I'm going to write out the coefficients of x squared minus 16. So I'm looking at the numerator, and the coefficients would be there's 1x squared, there's 0x, and then the constant term is negative 16. Going to perform this synthetic division. So remember, the 1 comes straight down, then you multiply the value up here in the corner here by this 1, so 2 times 1 is 2, add going straight down, then you're going to multiply your result by this number in the corner again, you get 4, you add straight down, negative 12, that's the remainder. But the important thing here is that these coefficients that we're left with here, this 1 and this 2, those are the coefficients of my end behavior asymptote. So my end behavior asymptote is actually going to be 1x plus 2. Or I could just write that as x plus 2. Great, so that's sort of the case where you need to do the most work for your end behavior asymptote. When the degree of the numerator is greater than the degree of the denominator, you actually have to do some division. So now, let's get all of this information on the graph. So I'm just going to sort of zoom out here so I can have the graph and all my information on the screen at the same time. So let's stash in those asymptotes. I've got a vertical asymptote at x equals 2. And my end behavior asymptote is y equals x plus 2. So that's a line with a slope of 1 and a y-intercept of 2. So just make sure when you dash in this line that you're dashing in a line with a slope of 1. There we go. Now I'm going to plot the points, the x-intercepts and the y-intercept. So I've got an x-intercept at 4, 0, an x-intercept at negative 4, 0, and a y-intercept of 0, 8. So the function's going to, in the long run, it gets close to those asymptotes. It has to go through those points. So I'm going to sketch out my graph. Looks something like that. And if I wanted a more accurate picture, I could get more points if I wanted to make a table. But that's a pretty good sketch. I've got all of the intercepts. I've dashed in the asymptotes. And I've as neatly as I can on the iPad, drawn in the sketch. And great. So that's another example of graphing rational functions, and good luck with the rest of your examples.